Hello, my name is Hayley, and I'm going to be discussing the research paper which investigates how the ant colonization optimization algorithm can be applied to the parallel drone scheduling traveling salesman problem, which I'll be referring to as the PDS-TSP. In the modern world, delivery systems have been forced to adapt in order to deliver goods throughout urban areas. One evolution in logistics has been the involvement of drones in the delivery process, which is an idea that has been adopted by many courier companies already, such as Amazon and DHL. Drones offer many advantages such as automated control, aerial transportation, speed, and they are also inexpensive. Clearly, the use of aerial transportation offers a range of possibilities, however, there are also limitations in which cause many new challenges to arise. These challenges are caused by the small size, narrow operating range, and short battery life of the drones. The parallel drone scheduling traveling salesman problem describes a version using vehicles and drones in combination where a vehicle is sent out from the depot along with a fleet of drones. The purpose of the vehicle is that it is used to reach customers that are too far away from the depot for the drones to access. The vehicle performs a regular delivery route, but the drones make trips directly to a destination and then return directly to the depot. The PDS-TSP solution was developed as a means to minimize the completion time in which all the drones in the vehicles return to the depot. This paper proposes an algorithm to solve the PDS-TSP by using hybrid ant colony optimization. I'm just going to give a definition of the PDS-TSP to gain a better understanding. So a complete undirected graph has a set of nodes where node 0 is the delivery depot and the remaining nodes are the customers, which are linked by edges. A truck and a set of identical drones are located at node 0. Firstly, the truck leaves the depot to service a subset of the customers before returning, and then the drones are used to service the remaining customers. However, the drones are limited due to practical constraints such as size of the package and how far they're able to travel. The PDS-TSP has two main processes involved. The first is the allocation of the customers between the vehicles and the drones, and the second is the optimization of the truck's route. For a comparison here, here's the original TSP problem, the PDS-TSP problem, and then also the FS-TSP problem, which is a variation on the PDS-TSP, which allows the drones to leave from the trucks as well as originating from the depot. The proposed algorithm is based upon ant colony optimization, which is a meta-heuristic technique which uses a set of software agents referred to as artificial ants in order to solve optimization problems such as finding the best path through a weighted graph. This technique incrementally constructs solutions based upon a pheromone model. This is a set of parameters whose values are modified at runtime by the ants and represent the experience of the colony. To gain a better understanding into the ACO, I'm just going to provide an example of how it is applied to a regular TSP. Looking at the graph here, all the cities are associated with a node, and the length of the edges correlates to the distance between the cities. The graph is completely connected, and the pheromone values and heuristic values are associated with the edges of the graph. The heuristic values are dependent on the problem. In this case, they are the inverse lengths of the edges. So each ant starts at a random node, and at each step they move along an edge. The ants have a memory, so they don't repeatedly visit nodes, and the solution is developed once an ant has visited every node. The ant chooses which edge it'll visit based upon the pheromone and heuristic values, so the higher they are, the more likely it is that the ant's going to travel along that edge. Once the tour of the graph is finished, the pheromone values are updated based upon the quality of the solutions to which it belongs. This continues until the termination requirements are met. Okay, so now moving on to the solution proposed in this paper, the meta-heuristic is actually broken into three main sections. So there's a section where the ants construct the PDS-TSP solutions, the local search operators, and the pheromone trail update. To begin, the algorithm consists of two pheromone trails, one to decide if a customer is assigned to a truck or a drone, which I'm going to call set A, and then another to find the customers to service next in the truck tour, which I'm going to call set B. Starting with the solution construction process, which collects all of the initial solutions for the problem, the pseudocode is presented on the slide. It begins with the process select drone node, whose purpose is to partially select a subset of customers to be serviced by the drones. Firstly, all the drone eligible customers are iterated over and selected with a set probability, and then this set is compared with a ratio of the customers retained from the current best solution based on their pheromone values of set A, and the best of these sets are chosen, and these customers will be combined with the customers selected to be serviced by the drones in the split procedure, which is further on in the solution construction process, which creates the final set of customers to be serviced by drones. This approach creates a balance between intensification and diversification, which results in a reduced number of customers considered in the next procedure, therefore minimizing the cost of the algorithm. Ant TSP Tour creates a giant TSP for the trucks to visit the depot and the remaining customers by nearest neighbor algorithm and roulette wheel selection using the pheromone values of set B. And then improved TSP improves upon this using 3-opt local search move. 3-opt local search move is a process which involves deleting edges to create 3 subtours and then analyzing the 7 different ways of reconnecting them to find the optimum tour. This is then repeated until all the combinations have been tested. Finally, in solution construction, the split function computes the best partition set between the truck and which customers are serviced by a unique drone, following the constraint that the customers serviced by the truck followed the same order as found in improved TSP. Each node from this TSP is assigned a label to represent the cost incurred by the truck, given that the cost incurred by the drone is less than or equal to a percentage of the objective value of the current best solution. The labels are assigned following the order of the TSP tour, and from each label, a truck path and a set of customers which are serviced by the drone is derived. For the drone service customers, a greedy heuristic is used to sort the customers into decreasing order of their processing time. Then they are successively aligned to the drone with the least flying time. The initial solution for the algorithm has now been derived. To provide a mechanism in the algorithm which prepares bad drone customer assignments, they implemented 2 local search operators, swap truck drone and swap drone drone. The first swaps a customer serviced by a truck with one serviced by a drone in an attempt for a better solution, and the latter implements the same between 2 customers both serviced by drones. The swap is then verified if it creates a saving in the objective function. The pheromone trail update updates the value of the tour using a smooth max-min ant system method to ensure the algorithm is leading to an optimized value. To test their algorithm, the creators ensured that the tests were run on similar processes to those algorithms they were comparing the HACO to. They justified their choices for all the parameters and presented them in this table with the objective to balance the optimization of runtime and the solution. So they ran HACO algorithms 10 times, each for 300 seconds, and recorded the solutions for the first run, the best solution, the worst solution, and the average solution. The table here summarizes the results of running the HACO algorithm against 2 existing solutions over 6 different problem instances. It can be seen that HACO performs just as well, if not better, than the other algorithms, and the average gaps are small, meaning that there were little fluctuations over the 10 runs, demonstrating strong stability of the algorithm. They then conducted Kruskal-Wallis one-way analysis of the variance in an attempt to find the clear best performing algorithm, and they produced a second table. In this analysis, the first rank is assigned to the smallest value, which by looking at the table is the HACO algorithm. Even though during the experiment they kept the algorithm running for 300 seconds each time they tested it, the algorithm often finished before this time, meaning it had a very optimized runtime. In conclusion, it can be seen that the approach taken in this research clearly outperforms that of previous ones in both terms of solutions and runtime. The authors have taken the ACO algorithm and combined it with the large neighborhood search and local search-based meta-heuristics, which provides a strong base foundation for solving the PDS-TSP problem. Their method takes into account the optimization of both the split between drones and trucks and the route of the truck. To achieve the best results in both of these characteristics, after creating an initial solution using 3 distinct processes, they refine it further while still taking the runtime into consideration. There are hopes that through further development, this algorithm could be adapted to provide a strong solution means to solving the FSTSP problem. In regards to what I liked and didn't like about the paper, starting with what I think could be improved, I found that at the beginning of the paper, too much time was spent on topics that I considered unnecessary, that more so confused me rather than helped me understand what the paper was about. For example, they spent a lot of time explaining the FSTSP, which I got confused between the characteristics of this algorithm and the PDS-TSP as they're very similar. I also think too much time was spent briefly describing a range of previous approaches, and this should have been limited to the approaches which they compared their actual algorithm to in the experimental results. I think that the time spent on this should have instead been used to describe the ACO, as I found I had to do extra research on this as I was unfamiliar with it, and they didn't explain it in any detail, regardless of the fact that it was the basis of their research and their algorithm. However, I do think the explanation of their meta-heuristics approach was done really well. It was broken down into manageable sections, and I liked their explanation of the PDS-TSP. I also thought the results were very clear, and I liked how they tested their algorithm under similar conditions as possible to previous approaches and tested a range of scenarios, and all the findings were presented very clearly. Thank you for listening to my Spotlight talk.